Hello students, we have come to the second part of the molecular stereochemistry lecture. I believe the first lecture on conformational analysis would be a little bit confusing for quite a number of you. So my suggestion is, if you still find some of the concepts challenging, you might want to review the video again, or to look through your notes and to practice the drawing. Okay, this particular lecture, the second lecture, is easier to assimilate because it's related to most of the things you have already studied. But probably one added point would be the naming, the naming of the configuration. Okay, so we'll begin with section 3 on cis-trans isomerism. Okay, so I will not attempt to go through all this because they are quite similar to what you have learned in H2. So basically, cis-trans isomerism arises due to the restricted bond rotation about the CC double bond, and the restricted bond rotation is largely due to the presence of the pi bond. Okay, so the pi bond sort of restrict the rotation. In order for bond rotation to take place, you need to overcome the pi bond, and I think it's given here that the typical amount of energy you need to incorporate will be about 280 kilojoules per mole of the pi bonds present. Okay, so therefore no restricted bond rotations about the CC pi bond, unless of course the amount of energy, this amount of energy, is applied to the system. Later on in reaction mechanism, you will also encounter something known as the concept of resonance. Okay, where delocalization of lone pairs of electrons across the pi system will actually make the single bond having a partial double bond character. So the partial double bond character will also restrict free bond rotation. A very classic example that most of you know, especially the bio students, will be peptide linkage, or in chemistry we call it the amide linkage. So the amide linkage looks something like this. So you have an N, they have a lone pair here, and of course sorry, I think I drew it like that, it's easier. The H, and then with a lone pairs of electrons, and then C double bond O. Okay, and then this is the amide. This is the amide or the peptide linkage. Okay, so this lone pairs of electrons resides largely on the p orbital, so it will overlap side on with the CO pi system. So this overlaps, this side on overlap will result in a partial double bond character between C and nitrogen. Yeah, so this partial double bond character actually restricts the bond rotation about Cn. Yeah, so in biology, some of you might be familiar with something known as the Ramachandran angle between the two planes, the NH plane and the CO plane. Yeah, so the reason for that is actually due to the lone pairs of electrons delocalized across the Cn bond. Okay, of course across the CO double bond as well. Okay, yep. So I'm going to move on to this portion where you are again very familiar, the difference between cis but2-in and trans but2-in. Okay, of course the main thing here we want to discuss is really the easy convention, or naming them as either the E or the Z isomers. Alright, so you know that for cis-trans, we normally can provide the name as cis or trans because the groups in question are similar. So for example, cis but2-in is because the two hydrogen are on the same sides. For trans but2-in, they are on opposite sides. Yeah, but what if we have atoms that are totally different from one another? For example, in our compound here, 3 chloropens 2-in. You notice that the 4 groups are different: hydrogen, chlorine, and then you have a methyl and an ethyl group. So how do we actually use the, how do we actually name them? So we name them through what we call the CIP rule, and this is the portion that a lot of students have misconceptions, so I thought I just want to highlight. Okay, the CIP rule, right, is based on atomic numbers, not molecular mass. Okay, so some of the students actually thought that they need to sum up the molecular or rather sum up the atomic number of the individual atom, and then the bigger it is, the greater the priority. Yeah, that may work most of the time, but by definition, we are looking at the atomic number of the atoms directly bonded to the CC double bond in this case. Okay, right, so please remember this. So in this case, for 3 chloropens 2-in, right, hydrogen's atomic number is 1. Chlorine, if you look through, is actually 17, and then of course carbon will be 6 and 6. Okay, now you might be wondering, the carbon both are 6, then how? What shall we do? Shall we sum up the atomic number, or what? Or shall we move on to the atomic mass? Okay, so that's what we'll discuss later on. Okay, now so for the priority rules, this is the case. Okay, so an atom with a higher atomic number has a higher priority. Okay, so this is clear cut. So in our case here, for example, hydrogen is 1, carbon is 6. Okay, so carbon is 6, chlorine is 17. Okay, so between the two, the one with the higher priority is carbon, and of course between methyl and chlorine, the one with a higher priority is chlorine. So because they are on opposite sides, okay, we will give it, we'll call it E. It's just by convention. Okay, of course we are not naming here right now, but just take note that if they are on opposite side, we'll call it E, same side we'll call it Z. Okay, yeah, so this part of the lecture notes haven't gone into the naming yet. The naming actually comes maybe in the second half or in the following page. Okay, but what we are looking at right now is the assignment of the priority. Okay, so what if there is a tie between the two? So what do we mean by a tie between the two? So for example, let me just highlight. Now okay, so for example, this is a CC double bond, or the sp2 hybridized carbon. So you have a carbon bonded and a carbon bonded. Yeah, so now there is a tie, right? So what do we do if there is a tie? Okay, so the easiest way is really to look at the next 3 atoms bonded to it, and then we will move along until there is a difference being found. Okay, so for example, this isopropyl group, right? I'm going to write down the 3 atoms in terms of decreasing atomic number. So I'm going to have C, C, and H. Okay, over here. Okay, so this is the C, C, and H. And then for ethyl, I'm going to have C, H, H. Okay, so what we're going to do here is we will just go across. So there is a tie here, but in this case, carbon has a larger atomic number as compared to hydrogen. So in this case, isopropyl groups will have a higher priority as compared to an ethyl group. Okay, so the same case goes for this particular one. So the tie is actually at the oxygen. So oxygen, there's a tie. Okay, then when we look at the first group, there's a fluorine here. So fluorine has a greater atomic number than hydrogen. So therefore, this group has a larger priority. Okay. What if it is joined to a CC double bond? Okay, so when it's joined to a CC double bond, we'll just so-called expand the double bond into single bond. So for example, this carbon, right, is double bond to a carbon next to it. So in this case, we'll expand it to 2 carbons, 1 and 2. And then same case goes for this carbon, we'll just expand it, and then there's another carbon here. So again, and then after that, we will make a difference. There will be a difference at the end of the day, and then that is how we will assign the priority. Okay, now this is actually the German term. So if the higher priority groups are on the same side, we call it Z. Okay, as what we mentioned earlier on. So if higher priority group on the same side, we call it the Z isomer. If they are on opposite, we call it E. Okay, so these are German terms. I will not attempt to pronounce the German names, so I'll just leave it up to you whether you want to find out how they are being pronounced. Okay, yeah. So we're going to move on to exercise 3. Yeah. So you're supposed to arrange the following groups in order of priority. Okay, so this is really not difficult. It's actually very mechanical. So some of you might find that it is quite boring. Yeah, I mean, I can sort of agree, or maybe I might disagree, I'm not sure, because it's indeed boring, and I'm definitely not one that particularly like to do namings. Yeah, but truth to be told, this is part of the curriculum, so I guess we have to go through that. Okay, so now there are so many groups, right? So I think the first thing is we'll just seize out all those with the common atom, common first atom in this case. So we have carbon here, we have carbon here, we have carbon here, and we have carbon here. Okay, so all these are the carbons. So carbon has an atomic number of 6. Okay, now so not very inspiring, because actually amongst all the rest, it has the lowest atomic number, because the remaining one will be oxygen, and then this is followed by nitrogen. Okay, so in terms of atomic number, oxygen is the greatest, followed by nitrogen, followed by carbon. Okay, so therefore the group with the greatest or with the largest priority, or rather with the highest priority, right? It should be the one containing oxygen. Okay, so it's either OCH3 or OCH2Cl. Okay, but of course, some of you might be very sharp because for OCH3 or OCH2Cl, right, the next atom is carbon. So again, you can't differentiate them. But moving on, right, for OCH3, the one with the highest priority next is hydrogen. But for OCH2Cl, the one with the next highest priority is chlorine. Okay, so this OCH2Cl will have the highest priority. So in this case, I'm going to write OCH2Cl and then CH3. Okay, so it will be in this particular order. And then because nitrogen has no competing atoms, so nitrogen will be next. Okay, and HCH2CH3. Okay, and then we'll look at the remaining ones. I'm going to write in green. Okay, so the remaining one will be relatively straightforward, I hoped. Okay, so these are the ones: CH2OH, CH2CH3, CH2Cl, and COCH3. In case you're not sure what is COCH3, is C double bond O CH3. Okay, yeah. So right now, we are just going to look at the next atom that's going to make a difference. Okay, now for CH2OH, right, it will be OH. Okay, if you try to expand it out. Okay, for CH2CH3, if you expand it out, it will be CHH. Then for CH2Cl, it will be ClH. And then of course for the ketone, it will be O carbon. Okay, so I think in this case it's quite obvious. If you look at if you just look at the first column, the one with the chlorine will have the highest priority. Okay, so in this case I'm going to write it as CH2Cl. Okay, and then of course moving on, what is the one with the next higher priority? I'm just going to continue here. Okay, the one with the next higher priority should be the one containing oxygen. Okay, it should be the ketone, because the ketone we can differentiate at the second atom. So that is the oxygen has a greater priority than hydrogen. Yep. So the next one should be COCH3, and this is followed by CH2OH, and then of course followed by ethyl, which is CH2CH3. Okay, so I hope with this short exercise you are able to see how we are able to assign priority quite easily based on atomic number. Remember, it's atomic number, not atomic mass. Okay, we are going to move on to exercise 3, question 2. Okay, so we are supposed to assign the correct letter to each of the following alkene. Okay, so again, E or Z. So the first thing we might want to do is to assign priority, of course. Okay, so based on our earlier experience, although they are all carbons, but ethyl group should have a greater priority as compared to methyl group, because the differentiating first atom is actually carbon rather than hydrogen. Okay, and because they are on opposite sides, we will assign it to be E configuration, or to have the E configuration. Okay, yeah, so we're going to do the same thing here. So ethyl will have a higher priority as compared to CH3, and then of course between the two, Cl obviously has a greater atomic number as compared to carbon. Okay, so the two higher priority groups are on the same side, so we will designate it as Z. Okay, so we'll do the same thing. So again, between H and carbon has a greater priority. Okay, and then of course here we have a Cl. Cl has a larger atomic number as compared to oxygen, so again they are on the same side, so again we'll designate it as Z. Okay, then between these two, chlorine will have a greater priority. Okay, so in this case, this is the one with the greater priority. And then of course for CHO, what exactly is a CHO? So CHO is like this, C double bond OH. So therefore for this aldehyde group, it will be written as O, and H. Okay, what about for this? Okay, so for this case, it's a carbon, right? Okay, is bonded to hydrogen, bonded to oxygen and carbon. So we'll write it as O, C, and H. Okay, so in this case, the differentiating atom is the second one. Okay, so oxygen has a greater priority as compared to carbon. So, and they're on opposite sides. So we'll designate this as E. Okay, so this is how we do the designation. So number one, if you want me to summarize it, the first thing you need to do is to assign priority. Okay, after assigning priority, then you can assign them the correct configuration. Yeah, the same thing actually works with Enantiomerism as well. Okay, but we'll talk about it later. So we'll move on to 3.2, other system that exhibit cis-trans isomerism. Yeah, so you might have encountered this in H2. So we are not only expecting CC double bond, so anything with a pi system is likely to exhibit cis-trans isomerism if the sp2 hybridized carbon is bonded to unique groups. Yeah, so for example, in our case here, this butanol oxide, right? This is designated as a Z isomer. Why is that the case? Because lone pairs of electrons, we do not give it an atomic number, of course, so it's like it will have a lower priority as compared to oxygen. And then of course in this case, the ethyl group will have a greater priority as compared to a methyl group. Yeah, so the higher priority groups are on the same side, so we designate this as Z. Okay, so so and so forth, it's the same thing. What about ring system? Yes, ring system have restricted bond rotation as well. Yeah, however, in most cases, right, ring system tends to give rise to another form of stereoisomerism. It's usually what we call enantiomerism. Yeah, so in this case, we will not actually attempt to give it E or Z naming, but of course in this case, just for illustration purposes, if they are on the same side, we call it Z, opposite side we call it E. But you will notice that in most cases, especially for this kind of system that does not involve CC double bond, we will tend not to give it the easy configuration. We will tend to give it the RS configuration if there's a need to. Yeah, just to take note of it. Okay, and of course, CC double bond can exist between two rings, or rather, this is between two rings, and this is between a ring and some other groups. So yep, this is possible. So if that happens, then again we will designate it accordingly. Yeah, how do we actually designate this? Sometimes the students might find it a little bit challenging. Again, we'll move until there is a difference. So in this case, between carbon and H, carbon has a larger priority. Yeah, but as we move along this side, it's a bit difficult to see. So this carbon is carbon, so same, and HH. So this carbon is carbon. So this carbon will be able to differentiate because this particular carbon is bonded to 2 carbon and 1 H, but this particular carbon is bonded to 1 carbon and 2 H. So in this case, the differentiating factor here, so this portion have a greater priority, so they are on opposite sides. So we will designate it as E. Okay, yeah, so it's quite straightforward if you really want to look at it, but I think it takes a little bit of practice for you to get familiar, to be familiar with the how to determine the priority, and followed by how to give it its configuration. Yeah, some students get confused between E and Z. Yeah, because it seems that opposite side they call it E, but opposite side looks more like Z, so they might just get confused and call it Z. Yeah, so in this case, you might just want to tell you that if they are opposite side, they look like Z, but it's not Z, it's called E, something along those lines. I think it will help you a lot in remembering whether is it E or Z. Okay, so the next segment, which is section 4, we're going to look at is Enantiomerism and Diastereomerism. So again, chiral molecules is not unfamiliar. You have gone through it in H2. Okay, yeah, so non-superimposable mirror image, basically like an internal plane of symmetry or a center of symmetry. This is very important because as I mentioned or illustrated in lecture 1, in the beginning of lecture 1, a molecule that is able to demonstrate enantiomerism, right, it need not have a chiral center. It is not a requirement. Yeah, so I think it takes a bit of maybe it takes a bit of time for you to understand that. Yeah, if you go on to university, you will actually get to learn point group symmetry. So once you learn point group symmetry, there will be a higher order definition for enantiomerism, but we'll not go into that. Okay, so this particular page is basically just to illustrate to you what exactly do we mean by a plane of symmetry, what exactly do we mean by a center of symmetry. Okay, I think that I don't need to illustrate any further, because anything beyond this will not be largely in this curriculum. Okay, of course we can do an enrichment on this, but in our case here, it might not be necessary for this lecture, because the lecture is mainly for you to pick up the necessary knowledge. Okay, yeah, so I think this demonstration of drawing the mirror image based on the original molecule is not new to you. You have gone through it in H2, so I don't think I will discuss this any further. Yeah, but if the atom contains the same group, or the same atom, or rather if the molecule contains or the carbon, okay, is bonded to atoms that are the same, then it is possible to superimpose the mirror image onto itself. Yeah, so in this case, we say that mirror image and itself superimposable, so it does not demonstrate enantiomerism. Okay, so basically enantiomers are stereoisomers that are non-superimposable mirror images of one another. Yeah, this is generic again, I mentioned. Usually contains chiral center with 4 different groups, but it's not always the case. Okay, yeah. There are a few points to take note. Sometimes we often use that in our lectures or in exam questions. Not all chiral centers are not all molecules with chiral centers are optically active or chiral. Okay, so one example is Meso compound. So Meso compound has an internal plane of symmetry. So with an internal plane of symmetry, then mirror image and itself will be superimposable. Yeah, and then there are a few terms that you should not be confused with. For example, asymmetric center. Asymmetric center is almost synonymous with chiral center, so you might want to be familiar with this term. Stereo center and stereogenic center. Okay, it's an atom at which the interchange of 2 groups produce a stereoisomer. Yeah, so I think once we started on reaction mechanism, you'll be more familiar with this term. Other than that, I think we don't want you to be too stressed over these terms, because sometimes when you are very stressed over the terms, it might inhibit your learning. Okay, so I think just read through them, and then maybe just know that they exist, and then after that come back and revisit them. Okay, you have learned this in H2 as well. A pair of enantiomers usually undergo the same kind of chemical reactions. Okay, of course this is provided that the reagents are non-chiral. I think this is not mentioned in H2. Yeah, you might want to be aware of it because in H3 occasionally you will be taught, or you might encounter this term known as asymmetric synthesis. Okay, where we are trying to make molecules that have multiple chiral centers. Yeah, so sometimes we use a chiral reagent or a chiral catalyst in order to create new chiral centers. So something like this might not be very familiar with a lot of you. So I think you might want to be aware of this term. I mean, like, yes, enantiomer undergoes the same chemical reaction, but that's provided that the reagents is non-chiral or does not have a chiral centers. Yeah, physical property the same, except their effect on non-polarized light. Yeah, and because they rotate plane polarized light, so this is a phenomenon of an optical activity. So we say that one of the terms used in the old syllabus is also optical isomers, and normally we rotate plane polarized, or we measure the optical activity using polarimeter. Okay, so you might want to be familiar with the drawing of this, especially in H2 . Not to say that in exam it will come out, but I think it is important to know how it works. Okay, so if you are interested, you might want to revisit one of the recorded lectures on introductory organic chem on optical isomerism or optical activity, because I think in the lecture there were some videos demonstrating the rotation of plane polarized lights. Okay, so yeah, basically this rotation of plane polarized light is more of how the electron clouds of the asymmetric of the molecule, right, interacts with the photons from the light. Yeah, so if the electron cloud is asymmetrical, or they are chiral, then the interaction will cause the photons to rotate in a certain direction. Okay, yeah. Then I think these are things you might have encountered in H2. Probably the one that might be a little bit interesting will be this part. So enantiomer that rotates the plane polarized light to the left, so in this case anti-clockwise fashion, is what we call a levo isomer. Then the other way around to the right is called a dextro isomer. So you don't have to memorize this, but maybe good to know. Okay, the designation is minus and plus. Yeah, also good to know as well, I mean, but no need to memorize. Okay, so if it contains equal concentration of the two enantiomers, then you will get a reciproc mixture. So the rotation of plane polarized light will be cancelled off, and then eventually you end up with no rotation. I think you're familiar about that from your H2 knowledge. Okay, yep. So right now we are going to discuss the RS convention. The RS convention uses the same CIP rules in assigning priorities, which we discussed earlier on page 15. Okay, so let's take a look at the steps. Yep, so similarly to what we did for the easy configuration, we will apply the CIP rules to the 4 groups attached to the center carbon. Okay, in this case, I mean, in most cases we are dealing with carbon at least at a H3 level. Okay, then once we do that, we will put the group with the lowest priority away from our eyes. Okay, so for example, in this case, the group with the lowest priority will be put behind, and then we'll look at the groups with priority 1, 2, and 3. Okay, if we go from 1 to 2 to 3 in a clockwise fashion, we will designate the chiral center as taking on a R configuration. If it's anti-clockwise, it will take on an S configuration. Okay, so something along those lines lah. Yeah, it's actually pretty straightforward, except that sometimes you need to visualize how you are placing the groups, and that usually have students usually find some issues dealing with all these lah. Okay, then okay, so for example, let's deal with this 1 bromo 1 chloroethane. Okay, so now for 1 bromo 1 chloroethane, right, for example, in this particular molecule, okay, so this is the chiral center, this is the carbon, right? Okay, so now, right, we're going to assign the priority. So we are looking at bromine, chlorine, carbon, and hydrogen. In terms of atomic number, of course, bromine has the highest priority. This is followed by chlorine, followed by carbon, and then of course hydrogen. So we are going to put our eyes here. So when we put our eyes here, bromine is here, chlorine is here, carbon is here. Yeah, so if we go from priority 1 to 2 to 3 is anti-clockwise, or rather it's clockwise, so this is a R configuration. Okay, then it's mirror image. Gonna put our eyes here, so the H is away, so priority 1, 2, and 3 in an anti-clockwise fashion, so it will be designated as S configuration. Yeah, so essentially this is how we assign configuration to the chiral center. Okay, so right now we have exercise 4. So in exercise 4, we are supposed to assign priorities to the 4 atoms, okay, or the groups around the central carbon or the chiral carbon, and then we're going to assign the chiral center to be R or S. Okay, so what we're going to do is we'll just do them one by one. Okay, so for this particular molecule, okay, so me see, I'm going to change to green. Right, so we have carbon, carbon, carbon. So H, of course, lowest priority, so number 4. Okay, then amongst all the carbon, if you are already quite familiar with how to assign priorities, you will notice that there's a Cl. The Cl stands out because Cl has the largest atomic number amongst carbon and hydrogen. So definitely CH2Cl, this group will be assigned priority 1. Okay, then for the other two, of course, CH3 will be priority 3. How do we know it's priority 3 and not priority 2? Because for CH3, the carbon is bonded to 3 H's, but for CH2CH3, the carbon is bonded to carbon, H and H. So if you look at CHH versus HHH, okay, you're going to differentiate them using the carbon, okay, for ethyl. So therefore, ethyl will take on priority 2. Yep. And right now, if we are going to place H away from us, okay, we're going to look at it this way. So 1, 2, and 3, this is anti-clockwise, so it will take on the S configuration. Okay, so that's how we can assign it relatively easily. Okay, now we'll do the same thing. Of course, H, lowest priority. Then again, we have CHO. So those of you who are familiar, oxygen has the greatest atomic number amongst oxygen, carbon, and hydrogen. So this is priority 1. Then of course, CH3 versus isopropyl, of course, CH3 priority 3 and this priority 2. So again, we put our eyes here. Okay, so we go from 1 to 2 to 3 and then back to 1. This is in this fashion. So anti-clockwise, so take on the S configuration. Okay, so S configuration. Okay, then again, the next molecule, because it's written this way, it's a lot easier, right? Because the H is away, so priority 4. Oxygen has a greater priority than carbon, so priority 1. Of course, between CH3 and carboxylic acid priority 2, and this is 3. Okay, so again, because H is already away, so very simply clockwise, so this takes on the R configuration. Okay, I'm just going to change to orange. Right, next. Okay, so this might be slightly more complicated, so let's try to do it slowly. So again, between chlorine, carbon, carbon, and carbon, chlorine has the highest atomic number, so priority 1. Okay, then what about CHO versus the rest? Okay, so we'll take a look at this. So this carbon is bonded to sulfur, so this will be sulfur H. Okay, for the other carbon is a double bond O, right? So it will be O, O, C. Okay, then the other carbon is double bond O and H. So this will be O, O, H. Okay, so in terms of priority, sulfur has a larger atomic number than oxygen, so this will take on priority 2. Then between aldehyde and ketone, the differentiating factor is the last atom. So this has carbon, the other one has H, so this is priority 3 and this is 4. Yeah, so because it's 4, we look below. So when we look below, it will look something like this. Okay, so group 3 will be here, group 2 will be here, group 1 will be here. So 1, 2, and 3 clockwise, so R configuration. Okay, yep. And the last molecule we're going to look at is this. So again, this is the chiral center. Hydrogen priority 4 because it has the lowest atomic number. Okay, and then of course methyl group here. Methyl group usually is the next lowest priority, so 3. How do we know actually? Because methyl is HHH. Okay, and then what about these two groups? Okay, so these two groups we have is CHH versus CCC. Okay, so this group priority will be 1. Okay, and then this will be 2. Okay, 2 over here. And then of course right now we are looking at anti-clockwise like this. Okay, because H is already away, so in this case it will take on the S configuration. Okay, so if you are wondering, do scientists or do chemists often go around assigning configuration? Actually no, we don't really do that so often, because in actual fact, if there are many chiral centers, then we don't want to spend our time keep looking at keep deciding which chiral center is this, is it R or S. Yeah, so the software ChemDraw, right, can actually help us assign the chiral center quite easily. So if you take a look at the last example, right, you'll notice that the H is projecting inwards, okay, and then of course the methyl group is projecting outwards like this, and then over here there are two methyl groups like this and like this, right? Okay, so if I'm just going to put the H in, okay, I can find out the chiral center quite easily. I just need to highlight this structure, and then I go to structure, convert structure to name, and it gives me the S configuration. Yeah, so it's quite amazing. Yeah, so the ChemDraw software can actually help us using AI, right, determine configuration quite easily. Okay, so again, if you want to test its capability, we'll use the fourth example. Okay, so the fourth example has an aldehyde here, right? CHO, and then there is also a ketone. Okay, so again, I'm just going to draw a ketone out. Okay, and then of course we have a group projecting towards me, and then of course this group contains sulfur, so it's S and CH3 here, and then a group projecting inwards, that will be a chlorine. Okay, so I'm just going to input the group, so this is a chlorine. Okay, and then I have a sulfur over here, and then of course, not to forget, I have oxygen here, and here. Okay, so I'm just going to highlight this, and then convert structure to name, and then indeed this is the R configuration. There's only one chiral center, so it's the R configuration. Yeah, so this actually help us to ensure that what we tell you, what we share with you is correct. Of course, if we are research scientists, we do research, we do synthesis of molecule, then when we want to publish papers, of course, if we want to, we can go through the CIP rules lah. But in actual fact, a researcher has a lot more things to do. For example, we would prefer to focus our discussion on the main interesting facts about the publication we are going to publish. Okay, so of course, when we do that, then we have less time to do other mundane things like naming. Okay, so in that case, we'll use ChemDraw to help us. Yeah, so this is just to share with everyone that we can actually use software to help us determine the RS configuration. We do not need a human to go and assign the RS, but of course, using AI is to help us verify whether our theory is correct, but it's vice versa, because the AI uses the theory we teach you. Okay, yeah, so but it's just faster in that sense lah. But there is a limitation to using artificial intelligence to assign RS configuration. There are some molecules that cannot be assigned. Okay, when we chance upon that, then we'll share with you. If not, then I think you can just forget about it for now. Okay, yeah, so we're going to move on with our lecture. Okay, 4.2, compounds containing more than one chiral center. So we have diastereomers. Okay, so diastereomers is not something that is extremely new, except that in H2 we do not emphasize on this particular term. Yeah, so diastereomers basically means the two, like, okay, I mean, we'll use an example. For example, compound A and B. Okay, so compound A and B, right? They are not enantiomeric pair. They are not an enantiomeric pair, but they are still stereoisomers of one another. Yeah, how do we know that? Because one of the chiral center is the same, the other chiral center is changed. Yeah, so because of that, we will say that they are still stereoisomers, but they are not mirror images, so we call them diastereomers. Yeah, so in short, so diastereomers are like non-mirror image stereoisomers, something along those lines lah. Yeah, so if you are sharp enough, you might also be able to tell that easy isomers are diastereomeric pair in that case. Okay, yeah. So over here, what I can share with you is that A and D are enantiomeric pair, B and C are enantiomeric pair, yeah, and then the rest of the combination are what we call diastereomeric pair. Okay, so I guess you just need to check it out. I think it is well illustrated over here. Okay, so in short, we have this particular definition. Diastereomers are stereoisomers that are not mirror image of each other. Okay, yep. So moving on, diastereomers have opposite configuration at some chiral centers. So I think that is an outcome that you are probably aware of. Similar chemical properties, but different physical properties. So physical properties can differ in terms of boiling point and melting point. Yeah. Chemical property is not exactly 100% the same. For example, when they react with a chiral reagent, the rates of reaction might be different. Yeah, because the activation barrier towards the product is slightly different. So it is the slight difference that gives rise to the preference for one product over the other. Yeah, but of course, we won't go into details over here. Right, so for exercise 5, I think the first thing we might want to do is to assign the configuration to each of the chiral centers. Okay, there is actually a quick way of doing it. Okay, so I'm just going to share with you what is the quick way of doing it. Yeah, so one way you can do it is you focus on the first compound, which is compound 1. Okay, you do it properly lah. Okay, so if we were to do it properly, then H will have the lowest priority, then of course oxygen highest priority, then CH3 usually is the third lowest, and then in this case we have CBr, so this is the second one. Okay, I mean this group is number 2 lah, but I think you guys know what I'm trying to say. Okay, so it's number 2. Yeah, then if we go from 1 to 2 to 3, we put our eyes here. So this is clockwise, so this will take on the R configuration. Okay, so we do the same here. This is number 4. Yeah, this is number 1, and this is number 3, and this is number 2, right? So we'll do the same thing. But in this case, we have to put our eyes over here. Yeah, so we'll go from 1 to 2 to 3. So this is 2, so 1 to 2 to 3, so it's R configuration as well. Okay, so if we understand that compound 1 is RR, then all we need to do is just to check across 2, 3, and 4. Yeah, so you notice that for 2, right, CH3, let me see, is there any swap in? Yes, CH3 and OH swap in position. Yeah, if we swap in position, it goes from R to S. Yeah, this is definite. Okay, and then of course, right over here, the BR, is there a swap in position? No, there's no swap in position. It's just a rotation about the CC bond. Okay, you notice that when I go from methyl to H to Br is clockwise, methyl to H to Br is also clockwise. So this is R. Okay, so this is SR. Okay, so we do the same check. This OH here, oh yeah, so this is just a rotation, so this is R configuration, and then of course we do the same thing. Essentially, the H is here, the Br and CH3 swap position, so this is S. Okay, and then of course this will be SS configuration. Yeah, so because of that, enantiomeric pair will be 1, okay, and 4. Okay, and then 2 and 3. Yeah, then diastereomeric pair will be the rest, so that will be 1 and 2, 1 and 3, and then 2 and 4, and then 3 and 4. Okay, that's about it. Yep, so in short, a quick way of doing such exercises is always to identify the chiral centers of the first molecule, and then the rest will be can be determined much more easily. Yeah, a quick way to ensure that you do not assign wrongly is just to double check. Okay, like earlier on, although there's a bond rotation, what I did was I just double check the order of the groups lah. Like for example, if I go from Br to CH3 to H, is it clockwise or anti-clockwise? Doesn't matter whether is it R or S. Yeah, so because we already assigned one, so once we check the other one, and nothing has changed, then we are on the right track, and we can simply just assign it as the configuration we determined earlier on. Okay, yep. And then for meso compounds, I do believe that for H2 you have briefly discussed what meso compounds are. Yeah, so basically meso compounds contains minimally 2 chiral centers, but it has an internal plane of symmetry. Yeah, and usually it is not very difficult to tell whether something is a meso compound or potentially can be a meso compound. What you need to do is just to check if the chiral center are bonded to the same group. Yeah, so in this case, for this particular molecule is Cl, CH3, and H. Yeah, because of that, potentially they can actually end up as a meso compound. Okay, so how do we actually sort of verify it? Okay, so you notice that we gave the configuration like RR, RS, SR, and SS quite similarly to what we did just now. But one thing we can do is we will try to do a rotation over here. So if we do a rotation sort of clockwise, then you notice that Cl will be found projecting away, okay, and then H will be found projecting up, and then CH3 will be found here. Yeah, and this compound do not have an internal plane of symmetry, so E is definitely not a meso compound. Okay, so E is not meso. Yeah. If you look at F, you will be able to tell that it's a meso compound, because if you do a rotation, CH3 is found here, Cl is projecting towards you, H is projecting away. Yeah, so this is a meso compound. In fact, F and G are the same compound if you look really hard at it. Okay, yeah, because if I'm going to again do a rotation, like if I just rotate it this way, Cl will be projecting away, H will be projecting towards you, and CH3 will be here. Yeah, and there's an internal plane of symmetry. But the internal plane of symmetry cannot be determined by the staggered configuration or conformation, sorry. It has to be determined when you do a bond rotation to end up with a eclipse conformation. Yeah, it's easier to tell. Okay, so this is meso as well. So this is not meso. Yeah. So because of that, if you look at F and G, they are actually the same compound. Yeah, so we'll say that F and G are the same thing, and they are known as meso compound. Okay, so meso compound means it has an internal plane of symmetry. Yeah, so the mirror image is the same as itself. Why is that the case? Because when you draw the mirror image out, both can be superimposed directly. Yeah, so this is an example of what we call a meso compound. Of course, if you look at our tutorials, there will be more questions on meso compound. So in that case, it's easier for you to practice. So after more practice, then you'll be more familiar. So remember that molecular stereochem, one of the ways to improve is to constantly think about molecules as 3-dimensional object, and then practice when given the opportunities. Okay, yeah, so this is the internal plane of symmetry. I think I'm not going to go into details because we have discussed quite a bit. Even I do believe at the H2 levels, some of the examples I mean you're familiar with. Okay, yeah, so I'm just going to go to the last section, or maybe the second last section, on stereochemical purity. Okay, so usually pharmaceutical products such as medicine, they are only one of the stereoisomers is active, so the other one is not active, or it could be poisonous. Yeah, so because of that, it is important for us to ensure that during our synthesis we are making the pharmacologically active one, and not the other one that is not active or turns out to be a poison. Yeah, normally we do not want to produce racemate mixture, because it will be a waste of half of it. Yeah, so imagine that only half of it is active, the other half not active. Then if we end up with a racemate mixture, we are actually wasting precious resources. Yeah, but asymmetric synthesis or synthetic strategy making enantiomerically pure compound is not easy. Yeah, it's not easy. So I mean, it has developed leaps and bounds for the past 30-40 years lah, but still there are difficulties in ensuring that still stereochemically pure products can be made. Okay, but the H3 curriculum is not a curriculum where we discuss a lot about asymmetric synthesis lah. So we don't want to go into details, but if you are interested, you can read about it. In university, this is usually a year 3 or year 4 course, yeah, in organic chemistry. Okay, so the process of doing asymmetric synthesis is what we call asymmetric induction, because the presence of one chiral center will allow the other chiral center to be formed in some preference. The reason is because if I already have one chiral center, in the process of producing the other chiral center, the transition states will be what we call a diastereomeric transition state. So diastereomers have different properties. So the diastereomeric transition state will have slightly different energies. Yeah, so it's this slight difference in energy that results in what we call asymmetric induction, and eventually one diastereomer is preferred over the other one. Yeah, so in the event that we get a mixture of, we get a racemic mixture, are we able to do separation? In some cases, if not in most cases, separation is possible. For the purpose of H3, we introduce you to this method known as enantiomer selective chromatography lah. Yeah, so basically as a racemic mixture flows through the column, one of the enantiomer prefer to attach it or prefer to form slightly stronger interaction with the stationary phase. The stationary phase used tends to be chiral as well, because it is only when it's chiral that it results in this kind of slight difference in interaction. Yeah, so because of that, then one of the enantiomer will flow faster than the other, and that is how separation can be achieved lah. Yeah, there are other methods as well. I think the last bit here we talk about fractional crystallization. So what exactly is fractional crystallization? So basically you are using maybe an enantiomerically pure base on acid, and then you let it undergo acid-base neutralization, maybe in this case with the acid that you want to separate, and then you get a salt. Yeah, the salt mixture is diastereomeric pair. Okay, but the salts may have different solubility in the solvent. Yeah, so the difference in solubility if you leverage on that, allows some form of separation to be taking place, and this is known as fractional crystallization. Okay, yeah, so some of these concepts are actually quite interesting, so if you are interested, you can read more about them. Okay, and then of course there's an example over here, but this is slightly different because this involves formation of an ester. Okay, so a new product is being formed, but of course in the formation of the ester, then you are getting a diastereomeric mixture, so one of them might be easier to be removed. We can also use enzymes to catalyze to produce one over the other. Okay, and then of course in this case we can also, let's say we have an ester that is a racemic mixture, we can use the enzyme to produce the hydrolysis product. Yeah, because in this case the enzyme reacts faster with one enantiomer rather than the other one. So in this case, the one that allows the enzyme to interact with properly, right, will be hydrolyzed to give you the alcohol, so the other one will remain unreacted. Then you notice that in this case, right, the alcohol form has the OH group projecting out towards you, and then the other one, the unreacted ester, remain as an ester. So this is quite beautiful because I can easily separate the alcohol out, and then for the unreacted ester I can just perform a global hydrolysis, and in that case I'm getting enantiomerically pure alcohols. Okay, and then this is some calculations for you, but very straightforward kind of calculation. Is what we call enantiomeric excess, or what we call optical purity. Yep. So basically it's the difference between the two isomers divided by the total amounts multiplied 100%. Okay, so in the past something is considered asymmetric something is considered to be successfully made via asymmetric synthesis when it has an enantiomeric excess of about 95% or even 90% in the much earlier years. Yeah, nowadays people are looking for enantiomeric excess, excess of 99% or even greater. So that means that for you to achieve enantiomeric excess of 99%, that means that you must have about 98% of R, maybe 2%, 99.5%. In fact, you want an enantiomeric excess of 99%, you must have 99.5% of R, 0.5% of S. Yeah, so if you do the calculation, that's how you get enantiomeric excess of 99%, and that is quite difficult to be achieved. Okay, so there's also something known as specific rotation. So the sample divided by the enantiomer. So in that case, you will be able to find out the purity of the sample. Okay, yeah. So I think mathematics here wouldn't pose much of a problem. And then of course there's a difference between conformation and configuration. Okay, so for conformation, it's basically rotating about single bonds. Yeah, so there are infinite number of conformation. Yeah, but if you want to change configuration, you can't just simply rotate. You have to break the bonds, literally break the bonds. Okay, of course you don't just break the bond as in like take out the model and then put in the other side lah. But you need to be able to find ways for the reaction to occur. So that's the key difference between conformation and configuration. That is something that sometimes confuses students lah. And then what about the importance of molecular stereochemistry? I think in JC1, under introductory organic chem, you are introduced thalidomide, which results in birth defects in the 50s and 60s, right? Yeah, so this is an example where one of the enantiomer is toxic. Yeah, okay, yeah, so I think you can easily read through, and in your assessment questions, there should be quite a bit of or rather in tutorial and assessment question, we will give you quite a bit of context related to either asymmetric synthesis, asymmetric induction, or even the importance of molecular stereochem. Why is it important? Yeah, because one of the isomers may be preferred in the body over the other, and maybe one of them will give you the pharmacological response but not the other. Okay, yeah, so with that, I think we have come to the end of the lecture on molecular stereochem. It seems a bit straightforward. Some of you might think that, you know, like it's quite easy to talk about it, and then the lecture seems quite smooth. But of course, doing the question is another level of complexity. Yeah, and of course, applying it at reaction mechanism, applying it after you learn all the topics will become way harder. Yeah, so I urge you to continue to work hard towards your H3 if you decide to continue with it, and the hardest chapter will be the next coming chapter on mechanism. Yeah, but before that, focus on improving on your drawing of your conformations or on the 3D drawing. Yeah, so these are the important things. So with that, we'll see you in the next topic.